And now it's time to take a look at other ways of determining concentration. Okay, easy peasy. Let's do this. First, molality. Why not? Let's do it. Molality is the moles of solute per kilogram of solvent. Now, if you're taking the Regents exam, you don't need to know this, but if you're in an advanced class, you may need to know this. This is opposed to molarity, which was moles of solute per liter of solution. The differences between the two methods of figuring out concentration: molarity, you know how much solution there is because it's moles per liter of solution. For molality, you know how much solvent there is because it's moles per kilogram of solvent. For molarity, because the amount of solution is fixed, the more solute you add, the less room there is for solvent. So the amount of solvent can vary depending on how much solute you add. For molality, the total volume of the solution will be whatever the volume of the solvent is plus whatever the volume of the solute is. So in molarity, you have a fixed volume of solution. In molality, you have a fixed volume of solvent. It's a subtle distinction, but it does make a distinction. So molarity and molality can be used for completely different things. For water, 1 kilogram of water will occupy 1 liter. So you can also say moles of solute per liter of water. So let's go ahead and do that. What is the molality of a solution that contains 30 grams of ammonium chloride dissolved into 500 grams of water? Well, first we have to convert the grams of ammonium chloride to moles. So let's take those grams and divide it by the gram formula mass. 14.0 plus 4 times 1.0 plus 35.5. And this adds up to 53.5 grams per mole. When you divide, the grams cancel and give you 0.561 moles. Again, 3 sig figs, 3 sig figs, 3 sig figs. Now we have moles. Great. Molality is moles per kilogram. We have gram. So we have to convert those 500 grams of water to kilograms by dividing by 1,000 grams per kilogram. Grams will cancel and give you, well, don't forget 3 sig figs, 3 sig figs. Now that we have moles and kilograms, we just simply divide them. Molality is moles per kilogram, so let's just take those moles and divide it by the number of kilograms of water, and that will give us our molality. So 3 sig figs, 3 sig figs, 3 sig figs. Now remember, with molarity, you could have just put moles per liter, or you could use a capital M. Here, you can leave it as moles per kilogram, or you can leave it as lowercase m. Lowercase m means molal, uppercase m means molar. I know, it's kind of like enthalpy and entropy all over again. Subtly different sounding words. It can get confusing, so just be aware. Okay, the remainder of this will be on the Regents exam. Parts per million. This is also on reference table T. Parts per million is the mass of solute divided by the mass of solution times a million. You know how percent is part over whole times 100? Well, parts per million is exactly the same thing. It's part over whole, but instead of multiplying by 100, you multiply by a million. So we use it to determine concentrations of things that have a very small concentration, like concentrations of contamination in the environment. So there are some things that are so dangerous to your health that you want to put an upper limit on how much is allowed to be in your drinking water, on the ground, in the air, stuff like that. They've actually done testing to see what is the maximum amount that there can be with the minimum amount of health hazard. And they've created a chart. The organization that's responsible for coming up with these numbers and enforcing it is the EPA, the Environmental Protection Agency. There are regulations on this. However, these numbers and what's regulated changes dramatically depending on which administration happens to be in office at any one given time. So these numbers are a sample only. It's possible that, let's say, the current administration has lifted restrictions on mercury and now allows zero point 0.5. And let's say the next administration comes in and says that's too high, we'll lower it to 0.001. So again, these numbers are variable because unfortunately, and this is the reality, policies are rarely dictated by actual science and data and are far more dictated by politics. Science should not be involved in politics, but unfortunately, that's just the way it works. So these are just representative numbers and may not be the case at the current time. These numbers could either be higher or lower. Now, let's say we test 200 grams of tap water and we find it to contain a certain amount of lead. When you buy a house, especially if it has a well, you need to test the water to make sure that it doesn't have any kind of contamination. Old pipes use lead in their solder that holds the pipes together. That lead can leach into the drinking water and make the drinking water unsafe. So you test the tap water, see how much lead there is, and then compare it to the standards. For these standards, 0.05 parts per million would be the maximum legal limit for lead. Anything higher than that, you would not be allowed to drink that water. So let's find out what its concentration is in parts per million. So parts per million is grams of solute, and that's 0.0050 grams. Let's pull that down. And the grams of solution is 200 grams. And then we're going to take that number and multiply it by 1,000,000, and we'll get 25 parts per million. 25 parts per million. The maximum legal limit was 0.05 parts per million. So this drinking water vastly exceeds the legal limit of lead in the drinking water, which means that you're probably not even going to be allowed to stay in this building because this is just not good. So that's how handy this is. Notice that this says 200 grams of tap water contains this many grams of lead ions, which means the mass of the lead ions is included in that 200 grams. That's why it's part over whole. But sometimes it may be worded slightly differently. For example, 2 grams of cadmium ions are added to 120 grams of distilled water. The way this is worded, that 120 grams does not contain that cadmium ions. The cadmium ions are 2 grams above and beyond that 120 grams. So you got to be careful with the way this is worded, because even though the mass of the solute is 2 grams, the mass of the whole solution would include both the solute and the solvent, which means the number that will go on the bottom is 122.0. So we're going to take those 2 grams of solute and we're going to divide it by the total mass of our solution and then multiply that by 1,000,000, and that will give us, that's a pretty big number. That will give us our parts per million. So sometimes the question will be worded in such a way that the mass of the solute is included with the mass of the solution. And sometimes it will be worded where they give you the mass of solute and solvent separately. So you have to make sure that you're putting the number on the bottom that is the mass of the entire solution. So if you have to add the mass of the solute and solvent together, make sure you do that before you do your division. Okay, let's rearrange the formula to find out how many grams there might be in a particular solution with a particular parts per million. So we want to find the mass of solute. So multiply both sides by mass of solution and divide both sides by 1,000,000, and you'll be left with mass of solute. So once again, we're going to multiply both sides by mass of solution and divide both sides by 1,000,000. Okay, so how many grams of nitrate ions will be found if you have 150? I don't like the way this is worded. It should say how many grams of a nitrate compound will be found if 150 grams of 200 part per million of this nitrate compound solution is evaporated to dryness. So we take this rearranged formula and plug in the values. So parts per million, there's 200 parts per million. Grams of solution, there's 150 grams of solution. Then we're going to divide that by a million, and we're going to get the number of grams of nitrate solution. Not nitrate ions, that would be wrong. Nitrate compound. Okay. Percent by mass and volume works exactly the same way, except instead of multiplying by a million when you're done, you just multiply by 100. So let's say we have a 200 milliliter sample of antifreeze and it contains 160 milliliters of ethylene glycol. What would the percent by volume of this ethylene glycol be in the antifreeze? So what we do is we take the volume of the part, we divide it by the volume of the whole, and we multiply by 100. So we have 160 milliliters of ethylene glycol for every 200 milliliters of solution. 160 divided by 200 times 100 will give us 80%. So 80% of the volume of our solution comes from ethylene glycol. You can do exactly the same thing with mass, except you'll be using grams instead of milliliters. And that's all there is to finding out the concentration of a solution. The final topic for this unit will be how the concentration of a solution changes its melting and boiling point. But until then, as always, bye.